All right, so we can get started. So, this is a little loud. Okay, so this is lecture 17 of Computer Science 162. So, still kind of loud. Goals for today. Maybe that's a little better. So we're going to talk about the socket API. So this is the interface between applications and the kernel for doing networking. And then we're going to talk about TCP. And TCP contains 4 important components that we're going to talk about today. The first being how you open a connection, the 3-way handshake that occurs. The second being reliable transfer. The third being when you're done with a connection, how you actually tear that connection down. And there's some interesting challenges. It seems like it'd be really simple, but it's actually a very complex problem. And then flow control. What we're not going to talk about is congestion control. And this is a plug for going across the hall and listening in on EE 122 if you want to learn about how congestion control works in TCP. So let's start with the socket API. So I have a bunch of applications. So I have Mozilla, I have Firefox rather, I have Thunderbird, and I have Skype. Okay, so web browser, email, and a video conferencing application. They use the socket API to talk to the transport layer, the transmission control protocol, and the user datagram protocol. All right, and then those two talk to the internet protocol layer, the network layer. Now, where do you think the socket API was invented? Wrong answer, sorry, not Stanford. Berkeley, right? Back in the 1980s, it was part of the Berkeley standard distribution. It is the most popular network API today in billions of devices, many, many billions of devices. Every smartphone supports the socket API. That projector with its little Ethernet cable supports the socket API. Laptops support the socket API. So it's in many different operating systems, including embedded operating systems. And then most languages support it. So obviously Java, Python, Perl, and so on all support the socket API. It's very similar to the file API that we have in Unix. So you actually have a socket descriptor, which is very similar to a file descriptor. It's a handle that gives you access to a socket. And then you can use read, write, and close system calls also on a socket. All right? Now, the transmission control protocol is built on top of the sockets layer. And it provides you with reliable, in order, at most once delivery. Okay, so lots of guarantees there. Yes?
When they were building the socket API, why didn't they build it on top of the file descriptor API?
So good question. When they were building the socket API, why didn't they build it on top of the file descriptor API? It shares a lot of commonalities in terms of the kinds of functions that you can do on a file handle. You can like open and close and read, you can do on a socket also. So it shares a lot of similarities. The difference is that there are some things that you want to do on sockets that are very different from what you would do on a file. You wouldn't wait for a file to appear, whereas with a socket, you'll wait for an incoming connection to appear. Or you'll make a connection to another remote machine. So there's some differences, and that's why it's not a perfect match. But a lot of the functions are actually shared between the two. Okay, so you get all these great things, right? Last week we heard about IP was best effort delivery, which means maybe you get the packet, maybe you don't, maybe it arrives in order, maybe it doesn't, maybe it gets folded, spindled, mutilated. Not with TCP. With TCP, you get the packet, it arrives in order, you only get it once, you don't get duplicates, and it will be delivered. It's also stream-oriented. So you can send arbitrary length messages across TCP. Whereas underlying that, IP is fixed size packets. Or I should say not fixed size packets, it's maximum sized packets. It also provides multiplexing and demultiplexing. So IP remembers between 2 machines. Right? Your machine has a unique IP address, my phone has another IP address, but there are many applications running on each one of those. TCP gives you the multiplexing and the multiplexing to let those different applications on both on my laptop and my smartphone talk to each other. Okay, so I could have a web server on my laptop and a web browser on my phone. I could have a mail server on my laptop and a mail client on my phone, and those both can work because TCP takes care of multiplexing and demultiplexing into IP. All right? And then you also get congestion and flow control. So congestion control is how we deal with the fact that, for example, if we're using a wireless network, it could be very crowded. And we want to fairly share that bandwidth across all of the different users of the network. So TCP tries to be fair when it's using the network. Then flow control is what we'll actually talk about today, and that's where I'm sending data at a high data rate from my laptop to my phone, or from my server to my phone, and this phone has a little bitty tiny RAM in it. So I don't want to overrun that buffer. And flow control is a way of the phone saying, hey, don't send me any more. And we'll see how that works. And then there's lots and lots and lots of applications that are built on top of TCP. All applications that want reliable communication. So you build things like chat. Right? You don't want to lose messages. So we can wonder about certain operating systems, whether they, certain mobile phone operating systems, whether they use TCP, because my messages always seem to get lost. File transfer, web browsing, all takes place over TCP. Any questions? Okay. So TCP as a service does the following things. First, we open the connection. There's a three-way handshake that occurs when we open the connection to set up that connection. Then we actually send our bytes. Right? And so again, bytes go from one tuple to another tuple. That tuple is the local IP address and local port to the remote IP address and the remote port. Now, I did say it provides this guarantee of reliable, in order, at most once delivery. But the real world is not perfect, and connections can fail. Right? So if I'm talking to the access point in this room and the power goes out, what are the odds of that happening? Then there's no way my packets are going to get through. And so when that happens, TCP will reset the connection. Right? So it's going to try, and it'll try, and it'll try. So even if I'm dealing with a noisy wireless network, the packets will eventually get through. But if it tries and tries and tries and can't get the data through, it resets the connection. So you'll see this with a web browser. You'll wait for a really slowly loading page, and then it'll say the connection was reset. That means TCP tried really hard and then gave up. Okay, and then when we're done, we tear down the connection. So let's go through each of these processes. So first, we want to open the connection. So our goal here is between, yes, question?
You mentioned that it can be of arbitrary length.
Yes.
How do we know when we're going to close? How would we ever close down if we don't?
So that's a very good question. These messages can be of arbitrary length, so how do we know when we can close the connection? That's why that's why we're going to actually spend some time talking about how you close the connection. And it's not, you would think it would be easy. You just say, okay, close the connection. But it's actually a lot more complicated under the covers. Okay, so first we're going to open the connection. So we need to agree on some parameters. And in particular, the parameter we need to agree on is the starting sequence number that we're going to use. Right? Now, the starting sequence number is going to be the sequence number of the first byte in the stream that we're going to send. All right? So this way, when we get bytes at the other end, we can tell whether packets, we can tell whether they're arriving in order or not. Okay? If we didn't know what the starting sequence number was, we'd have no way of knowing. Now, as a really simple security thing, and also to deal with repeated connections that I might make from one machine to another, we make the sequence numbers random. So hopefully that means we don't have collisions. I don't get a packet that was delayed in the network from a connection that I just had from a particular host. All right? Okay, so the way this works is the server, the application here, calls listen. Right? It says, I want to listen on a port. So if it's a web server, it says, I want to listen on port 80. If it's a server used to send mail, it says, I want to listen on port 25. If it's SSH server, it says I want to listen on port 22, and so on. All right? These are well-known numbers. If you go in your computer, if you have a Mac and you look in /etc/services, you'll see a list of all these well-known port numbers. Okay, at the client side, it says connect. right? So this is, you typed in, www.cs.berkeley.edu, and it connects to that machine on port 80. So it'll issue a connect. And the operating system will now send a special packet from the client to the server called a SYN packet. This contains its proposal for the first sequence number. So we picked this random number, X, and we sent it. So that message arrives here, and when it arrives, the server application gets notified that there's an incoming connection, and then it accepts that connection. And now once it accepts the connection, the operating system now will send back a message containing a SYN and ACK, and a sequence number Y, and an ACK X plus 1. Right? So why does it send X plus 1 back? Any ideas? Exactly. It means that we have received the connection. Right? We received the X. So we're sending it back to say, yes, I got your X. Right? And now I'm expecting X plus 1. It also sends a sequence number Y, because TCP is bidirectional. So we can send data from the server to the client, or from the client to the server. So we need to tell the other machine, the client here, what packets to expect from us. So it will expect Y plus 1 from us. Right? So once we get that, we now have to send another message, an acknowledgement, right, to say we got the SYN ACK. Right? So we send the SYN, we receive that, send back a SYN ACK, and then send back an ACK for the SYN ACK, right, with Y plus 1 to let it know we got it. Yes, in the back first?
If the sequence number is chosen randomly, what's to stop the max number, whatever you're storing it as, is being chosen, and then plus 1 ends up overflowing or something?
So the question is, what happens if you pick randomly your sequence number as the max, and then plus 1 causes it to overflow? So it wraps around. We'll see everything in networking is all about circular. So we assume it's modular arithmetic. Question? So why do we have to add 1 and not just respond with X or respond with Y? Because we tell it we've received and we're expecting the next one. So when we tell it Y plus 1, we're saying, OK, the next thing I'm expecting from you is Y plus 1. And same thing with the X plus 1. We'll see when we go through the various reliability protocols exactly how that gets worked. But it's basically we're saying what we expect next, not what we've received in this case. OK, so yes, question? Why not start with 0? So originally they did. And the problem is that what happens if I open a connection to your machine, and now I close the connection, and now I open another connection, right? And I do that really quickly. Then if packets get reordered in the network, you don't know whether the packets are coming in from the first connection or from the second connection. So by starting with a random sequence number, the idea is we start up offset, and that way we hopefully don't have overlap. Yes, question?
So a packet of actual data has not been sent yet.
That is absolutely correct. A packet of data has not been sent. Now, as an optimization, we can actually send data. We can send our HTTP GET request can go in this packet also, because the ACK is really small. It's just a bit that we flip in the packet. And the sequence number is pretty small also. Right? But we have added 1 round trip time, right? Because we have to wait for the message to go and the message to come back, and then we could actually send our data. So we're adding an extra delay. And this, in many cases, this won't be noticeable, but if you're operating over a satellite link, if you have some satellite internet service at home in the woods or something like that, then this could be significant. Now, the benefit, however, we do get from having this handshake is congestion control. That 40-byte packet that we send one way and we get back the response is a way of probing to see is the network congested. If that packet gets dropped, we know that the network is congested. It also acts against packets that might have been delayed and stuck in the network and might arrive after a previous connection has closed. Right? Make sure those packets have already gotten through the network before we now start sending data. OK, So this kind of agreement, agreeing on sequence numbers, this was pretty easy. So let's try a little bit harder problem. This problem is called the general's paradox. Right? Now, here's the constraints of the problem. We have two generals. Okay? One's on one mountain, one's on the other mountain. There's an army in the middle, and they want to attack that army. Now, each of the generals has a small army. Okay? So if they were to go and attack, they'd get slaughtered. Alone, they'd get slaughtered. But together, their army is larger than the army in the valley, and they would be victorious. So they can communicate using messengers. Right? So they can send a messenger through the valley to say something, and the other general can send a messenger back. Now, because there's an army in the middle, these messengers could be caught, captured, spindled, folded, mutilated, whatever. All right? So there's no guarantee that they'll get through. But we have a lot of messengers, right? Infinite supply. They're really cheap, okay? So the question now, I should say the problem now, is we need to coordinate our attack. Right? If one general attacks and then the other one, we fail. Right? Because if the first general attacks, he gets slaughtered. Then the other general comes down, gets slaughtered too. So they have to coordinate and attack at the same time, and then they'll win. Right? So this was named after Custer because he arrived at Little Bighorn a few days early and didn't survive. Now, infinite number of messengers, two generals, have to pick a time. Can we agree? Yes? No? I'll give you a hint. It's a paradox. Okay? So, we want to make sure that these two entities, and there's obviously an analogy here for computing, these two entities agree sending as many messages as they want back and forth on something. Those messages can be lost or corrupted. The answer is no, even if all the messages get through. This is why it's a paradox. Because you'd think if all the messages can go through, this should work, right? We should be able to agree on a time because we know the messages are going through. No messages are lost. Right? These messengers are really fast and sneaky. All right, so let's look at an example. All right, so first general, General A, says to General B, let's attack at 11 a.m. Sends the messenger. Okay? What do we know at this point? What does General A know? He knows he sent a message. Right? What does General B know at this point? That he got a message from General A saying, let's attack at 11. So he says, okay, yeah, let's attack at 11. All right, now what do we know? What does General A know? General B received the message and is okay to attack at 11. What does General B know? That he received the message at 11 a.m. was okay, and he sent a message saying 11 a.m. was okay. So can we attack? I hear no's. Why not? Exactly, because B doesn't know that A actually got this message. So B doesn't know, A might not have gotten the message, and so then B goes down and gets slaughtered. Right? And similarly, A knows that it got the message from B, but it also knows that B doesn't know that it got the message. So it doesn't know, is B really going to go? So, maybe it'll go down at 11 and get slaughtered, or maybe they'll both show up at 11 and they'll win. We can fix this, right? We send a message from A to B saying, okay, yeah, it's 11. Now we can attack, right? No? Why not? Exactly, right? A does not know if B actually got that message. And if B didn't get the message, then B still might not know that A got the message, so you can see. So we can fix this. We send another message, right? We can't, right? No matter how many messages we send back and forth, there's always this sort of trailing thing. And besides, it'll be after 11 anyway, and then we'll have to pick a new time. Okay, so this is the frustration, right? We can't know that the last message got through. Right, so why did I take this divergent path and start talking about the general's paradox? Because this is exactly the situation we run into with trying to close the connection. We don't know if that message we sent through saying let's close the connection actually got through. Now, because we don't want it to take an infinite amount of time to try and close our connections, we take a shortcut and we simplify it. It'll work in almost all cases, but not all cases. All right, so the goal here is we want to agree that we're going to close the connection. And oh, by the way, I should also say that we're going to look later on in the semester at a solution to the general's paradox that doesn't say when you're going to do something, but says whether you will do something or not. So you can't use it to agree to attack, but you could use it to agree to do something. No guarantees on when everybody will have actually done that, though. It's called two-phase commit. Okay, so we're going to do a four-way connection teardown process. So the first thing is the application on host 1 says close the connection. So it calls the closed system call. And that's going to send a fin packet for finish to host 2. Right, so now when host 2 gets this packet, it's going to send back a fin ACK. All right? Now, are we done? Not quite. Because all this has done is said that host 1 would like to close the connection. But remember, this is a bidirectional connection. So host 2, if this is a web server, might still be sending data. So there may be more data that comes down. Because host 2 is not done. Right? But at some point, host 2 will have finished sending all of its data. And now the application on host 2 will close the connection. Right? So now we send a fin packet in the other direction. Right? Are we done now? Not quite. Right? Because host 2 doesn't know that its fin actually got through. Right? So it's going to send back, host 1 rather, will send back a fin ACK. Right? Now, when host 2 gets the fin ACK, it knows the connection is closed. But does host 1 know the connection is closed? No. It's the same as the general's paradox, right? What if this message got lost? So for simplicity, we just wait a timeout period. We could try retransmitting the fin ACK, but instead, we just simply close the connection. So in most cases, this will work. In a few cases, it won't work, and you'll get a connection that kind of gets stuck in a weird state. All right? So that's closing. All right, so now let's switch gears and talk about, yes? So the question is there any way for host 1 to know whether or not the fin ACK got through? What does the class say? No, there's no way for us to guarantee, right? Because we could send back a fin ACK, right? And then we wouldn't know if that went through, and so then we'd have to send a fin ACK. We could just go back and forth. We would never know whether the one side would always kind of be left hanging, wondering if its message had gotten through. So this is the best we can do in the real world. And again, in 99.99999 something percent of the time, it works just fine. Occasionally, it'll get a little confused, and one side or the other might not have gotten it. So we could time out here also if we didn't send it. Now, why do we have to wait a timeout period? Because if it doesn't get back an ACK from the fin, it'll send another fin. And we want to make sure that that fin arrives here and the connection is still open. Because if we've already closed the connection when we get the fin, then we wouldn't be able to retransmit the fin ACK, because we would have gotten rid of all of the state. Once you close the connection, all the state is lost in the kernel. Yes?
What's the point of the last fin ACK? Why not, because once the host 2 sends its fin, it seems like it's not doing anything but waiting for this hypothetically never going to show up thing anyway. So why would you just have it time out as well? Or you could just close your
Yeah, so that's a very good question. When you send the fin, why don't we just simply mark the connection as closed on host 2 and throw everything away? The problem is that the fin could get lost, and then on the host 1 side, it would still think the connection was open. Right? So by retransmitting the fin, we're able to try and get it through, and then eventually we'll time out and reset the connection, which is effectively going to close it. Okay? Yeah?
Could you elaborate on like a case where this doesn't, where it actually ends up screwing up? Is there like a kind of common scenario where that would happen?
So the question is, can I elaborate on a case where this would screw up? So the thing is, where you could have a problem is if the FINAC just keeps getting lost. Right? So if the network connection is really bad, I'll send multiple fins, and then eventually I'll time out on the host 1 side, I'll time out on the host 2 side, and just mark the connection as closed.
But would that actually like end up having us lose any data?
No, so the question is, will we lose any data? No, because the data has already been sent here, and in just a few minutes we'll learn how we send the data reliably. And again, everything will work as long as we don't get into a pathological situation like the access point dies or an intermediate link completely fails and there's no route between the 2 hosts. In the back.
Is it possible to have a packet that would, like, if it got to a closed connection, would just come back? Could you, like,
Yeah.
bounce a packet off of a closed connection and they're not halfway?
No. So the question is, what happens if a packet arrives and the connection is closed? That's why we have to wait a timeout period. Because if the fin was sent and then the FINAC gets lost, right? So if we lose the FINAC, we're going to send another fin. And if we've already marked the connection as closed on host 1, then host 1 will say, I've never seen this before, and it'll just drop the packet on the floor. I don't know what connection this belongs to. So that's the reason why we wait this timeout period, is because that way we can retransmit the fin and still have the state in the kernel. But we want to clean up that state eventually. Right? If this is a web server and we're getting thousands of connections per minute, we want to make sure we're not going to use up all our socket space. So we want to close connections very timely. This is an attempt to try and do that. In the ideal case, the FINAC goes through very quickly, and we can mark it closed. Yes?
Is there any way to have the fin and the FINAX like have higher priority on the network, so the closing kind of commands are much less likely to be dropped because they kind of have more priority over just normal other packets?
Yeah, so the question is, could we have quality of service for these kinds of closed operations? The answer is, unfortunately, there isn't in IP. Everything is best effort. There's no prioritization. There have been lots of standards for having quality of service, but that's usually at the lower layers, at the link layer. So you may run into this timeout problem on the project. So when you're doing the last project, project 4, you're going to start up your, one of your servers listening on a particular port and try to connect to it. If you shut down the server and try to listen on the same port again, it may not let you because it's waiting for this timeout period in case there's any packets floating around. So you may have to change the number. Depends on the operating system how long the timeout is. Okay, yes?
How does host 2 know that all your data is transferred? Don't you need to act back from host 1?
You mean for the data?
Yeah.
Yeah, so we're going to go through exactly how we do reliable transfer on my next slide. Okay, any other questions? Yeah.
Why not, instead of just like dropping the fin after your close point, just like reply all fins
Oh, so why not just reply to, if you've already closed the connection, why not just reply with a FINAC to any incoming fins? That could be used for denial of service. It could cause you, to basically have to send packets back. So you could use it for an amplification attack. I could, take some very powerful server. I could spoof your IP address of your smartphone and send a FIN packet to the server with your IP address, and then it'll send the FINAC to you. And I could just send a few of these, and it'll just send a flood to you. So, redirection attacks and things like that are something you want to avoid. I think later on in the security part, we'll talk about some of the attacks that can happen on the handshake side that are also spoofing attacks. Okay, so any other questions? Okay, let's talk about how we actually get our data there. So we can do this. There's some simple parts of this. I mean, the basic concept here is if a packet doesn't make it through, we retransmit it. And we're going to number packets, we're going to number acknowledgments, so we can see if something goes missing. Our goal is to do this very efficiently. So we want to transmit whenever we can transmit, so we can move data as fast as possible. And we want to detect when a packet goes missing and be able to retransmit as quickly as possible. So we're going to look at two schemes. First scheme we'll look at is called stop and wait. And the second scheme is called sliding window. And we'll look at two different variants of sliding window. Right, stop and wait is just a toy protocol so we can understand how this works. Sliding windows is actually what's implemented in TCP. Okay, how does this work? So we use timeouts. So if a sender will time out if it doesn't receive an acknowledgement. So when I send a packet, I set a timer. And there's a lot of work that goes into figuring out how long should that timer be. Again, take EE122 if you want to know all the different algorithms that you use for computing how long to wait. Now, if you have every packet that the receiver gets, it's going to send an acknowledgement back. Right? So the sender can figure out if a packet goes missing because it'll see a gap in the sequence of acknowledgements that come back. Right? So I'm sending packets, the receiver's sending back ACKs. All right? Now, we have to be careful because the network is allowed to reorder, which means packet 1 could arrive before packet 2. So just because I see an acknowledgement for packet 2 doesn't mean, and I haven't seen one for packet 1, that packet 1 got lost. It could just be about to arrive. And then I get an acknowledgement for packet 1. This is one of the things that makes it a little complicated. The network is allowed to do anything to the packets. Now, another form of acknowledgement is called a negative acknowledgement. A negative acknowledgement is where the receiver says, I didn't receive a packet. So the receiver could either say, I did receive a particular packet, or it could say, I didn't receive a packet. Right? See, they're symmetric. I can say the same thing, right? I can either acknowledge a later packet, and that tells you you have a gap, or I can explicitly say, I didn't get a particular packet. So let's look at a very simple protocol just to start. All right, so this is called stop and wait, and we'll look at it without any errors occurring. Very, very simple. The sender sends a packet, waits for an acknowledgement. Repeat. Okay, so sender sends a packet, packet 1 to the receiver. Receiver sends back an acknowledgement. Right? That takes total time, round trip time. Right? Where the one-way time is D. That's the delay. Okay, so roughly, assuming the network is symmetric, the round trip time is twice the one-way delay. All right, or sort of you can think about it the other way around. If you measure the round trip time, the one-way delay is approximately half the round trip time. Okay, so time to get the packet out and back. All right, now we can send our second packet. Once that's received at the receiver, send back an acknowledgement for 2. Okay, so that takes another round trip time. Now we can send packet 3, and so on. Now, how many packets can you send? You can send 1 packet every round trip time. Right? Because here's 1 round trip time and we sent 1 packet. Here's another round trip time and we sent 1 packet. We'd have to wait for this to come back, and that would be another round trip time, and we'd send our 3rd packet. So we can now ask, what's the throughput? How many bytes are we getting from A to B, from our sender to receiver? Right? That's the number of bits that get delivered. So we need to make this a little bit more concrete. So let's pick some numbers. So just to be convenient, we're going to say the round trip time is 100 milliseconds. That makes the delay approximately 50 milliseconds. So one-way delay is half of that. And we're going to make our packets 1,500 bytes in size. Okay, so what's our throughput? Well, it's simply going to be how many bits can we get from A to B per second. Right? So it's going to be 1,500 bytes times 8 bits over 100 milliseconds. So we get 120 kilobits per second. So that's like dial-up speed, which is like twice dial-up speed, but it's pretty slow. Now, how fast are the links here? I didn't say, right? Because it doesn't matter. Right? And that's the problem. These links could be 1 gigabit links, they could be 40 gigabit links, and we're only going to get 120 kilobit per second out of those links. So that's not very good. We obviously want to do better. But this is a simple protocol just to explain, how this works. So now let's add errors, make it a little bit more complicated. So we wait and don't get an acknowledgement back because our acknowledgement actually gets lost. So how do we pick this timeout? Well, we're going to want to pick a timeout that's larger at least than the round trip time. In fact, you don't even want to make it close to the round trip time because remember, these networks can reorder and there's jitter, which means that your packet might arrive a little bit later, or if there was congestion on the network or something, or on a link. So we have to pick a larger timeout. It's called the retransmission timeout, RTO in TCP. And again, take 122 if you want to learn exactly all the algorithmic ideas behind picking that. So after a timeout occurs, we can retransmit. And now we'll get another acknowledgement, and hopefully that acknowledgement will go through. If it doesn't, we'll wait another timeout interval and retransmit again. And we'll just keep doing that until we finally give up and decide to reset the connection. Right? So that's the basics of what we're going to do here. Yes, question? No, so the receiver, the question is, does the receiver drop the packet after they get the second one? No, here the receiver successfully received the packet, and so here it's just going to send another acknowledgement. Right? It could already have taken and passed the packet up to the application because it arrived in order. Well, this will become a lot clearer when we look at sliding windows. Hopefully not too confusing. Yes? So remember, the question is, how would we know the RTT if the first packet never made it? So remember, we had that two-way handshake, right? So the SYN-ACK tells us roughly what the round-trip time is. And then we're going to pick a timeout that might be, a multiple of that, just in case, our SYN-ACK went through really quickly, but the network's kind of congested, and so packets are taking longer to get through. Yes. So the question is, wouldn't you have to receive the ACK first? And yes, when you send, remember, with the three-way handshake, I send a SYN, and then I get back a SYN-ACK. So that tells the sender now what the round-trip time is. If the SYN-ACK never made it, then we'll send another SYN. And we'll just keep trying until we get through. And then eventually we'll give up and declare, we can't connect to the host. Okay. So that was simple. Now I'm going to make it, unfortunately, really complicated. We're going to do sliding windows. So a window is just a set of adjacent sequence numbers. It's like 2, 3, 4, 5, 7, 8, 9, 10, 11. That's a window. They have to be adjacent. The size of the set is the window size. Okay, that's pretty easy. We're going to assume we start with a window size of n. So if A is the last acknowledged packet of the sender without gaps, right, so it's the last packet that we got in a continuous stream going back to the beginning of the connection, then the window of the sender is A plus 1, A plus 2, all the way up to A plus n. The sender can send packets in its window. Right, so this is at the sender, we keep track of what was the last packet we got acknowledged from the receiver, and what are the packets we haven't had acknowledged yet. Right? At the receiver, we maintain a window also. B is the last packet that the receiver has received without a gap. So B's window is then B plus 1 all the way up to B plus n. Now, the receiver can accept a packet that comes out of sequence as long as it's within its window. Right? So if it gets like b plus 1 and then it gets b plus 3 and the window size is 7, that's perfectly fine. It can accept b plus 3. Yes? The question is, how do we know there will be no gaps? There can be gaps. Right? This window, in fact, is everything before this window had no gaps. Right? So we successfully received all the packets in order up to this point. Right? Within this window, the packets could arrive out of order. We can't slide the window forward until we have b plus 1. Then we can slide it forward by 1. We get b plus 2, we can slide it forward again. But if we get b plus 4 and we haven't gotten b plus 1, we can't move the window yet. Right? You'll see this, hopefully it'll be a little bit clearer in just a moment. Yeah.
So does this mean that the packets are explicitly ordered? They're like explicitly numbered?
Yes. The question is, does this mean the packets are explicitly numbered? Yes. Every packet has to have a number. Right? We're going to change that later on, but for now, every packet has a number. Okay, so we'll keep it simple. Window size of 3. These are the unacknowledged packets within the sender's window. We're going to keep track of them over here. And over here, we're going to keep track of the out-of-sequence packets in the receiver's window. Now, first, let's look at what happens without errors. So we send a packet, 1, from the sender to the receiver. Okay, so now our window contains 1 packet. Then we send a second packet, because remember, we can send any, as long as it's within our window, we can send a packet. Right? So that means we can send packet 2. And in fact, our window is 3, so we can also send packet 3. Right? So now, as these get received, what happens? So the receiver receives packet 1. What's the receiver's window now? Nothing, right? Because we received 1 in order, so we can just pass it up to the application. We send back an acknowledgement. Right? Now, when we get the acknowledgement for 1 at the sender, what's our window now? 2, 3, 4. Right? Our window slides forward because we received the acknowledgement for 1, and this is only keeping track of unacknowledged packets. Right? So now we receive packet 2 here. We send back the acknowledgement. Our window slides forward 1 more, becomes 3, 4, 5. Okay, and again, we receive packet 3, and our window slides forward to 4, 5, 6. And we can send 6. Yes?
Shouldn't the windows on the right contain, like, is the case where I haven't received any packets basically saying I received no packets in order, so I'm now to look for packets in the window 1, 2, 3?
That's correct, right? So the window at the receiver is keeping track of packets that are arriving out of order. When you start the connection, there's no packets that have arrived. So if packet 1 arrives, that's the first packet you're expecting. If packet 3 arrived first, you'd have to put it in the window and wait. But there's no errors here. Everything's arriving in order, and so it goes nice and cleanly and smoothly. Yes?
So you're enforcing that the sender send everything in order, right?
No. The question is, are we enforcing that the sender send everything in order? No. It just happens, again, this is an example with no errors. Everything arrives in order. We'll see an example with errors in just a moment. But in this case, everything arrives in order. So it comes in, gets delivered to the application. The receiver doesn't have to maintain anything in terms of state. Yes? Question is, do the windows have to be the same size on both sides? No. And we'll actually see how, through flow control, the receiver actually controls the sender's, the window that they can use to send. Okay, so this keeps going, just back and forth, right? As the packets keep going, we can just keep sending. And we're never going to grow our window at the receiver because, in this case, all the packets are arriving in order. And at the sender, we're just going to slide our window forward, sending a packet every time we get an acknowledgement. Right? So now we can ask, what's our throughput? Well, in a round trip time, how many packets can we send? going to be W times the size of the packets over the round trip time. So we can have W packets in flight, right? We were able to send 1, 2, 3 before we got the acknowledgement for 1. Right? And then we sent 4, 5, 6 before we got the acknowledgement for 4. So each round trip time, we have 3 packets in flight now. Right? As opposed to stop and wait, which would be equivalent to basically a window size of 1. We're allowed to have 1 unacknowledged packet. Yes?
W was very big. So it happened that the run trip time sort of said first packet returned before we actually sent the full.
So the question is, if W was really, really large, could we get back acknowledgments before we had actually exhausted our window at the sender? Yes. Yeah. So now, there's kind of the question of how do we actually set W? And ideally, if we have a high-speed link, we want to match W to be appropriate for both that link and the round-trip time. Right? So let's assume we've got a link with a capacity of a gigabit. We've got a round-trip time of 80 milliseconds, and we've got a packet length of 1,000 bytes. So what do we want to make our window size be such that our throughput matches the link's capacity? So it's actually pretty simple. Remember, the throughput was the window size times the packet size over the round trip time. So that's simply going to be, we can flip that around by dividing out, and we get that W, the window size, is going to be C times the round trip time. So we just had multiplied to get that to the other side, and we divided by the packet size. Right? So this is going to be a gigabit times 80 milliseconds over 8,000 bits equals 10,000 packets. All right? So if we set our window size to 10,000, we will be perfectly aligned with the bandwidth of the link. Because every time we complete a round trip time, we'll have sent a gigabit, we'll have sent 10,000 packets worth of data, which will fill that gigabit link. Yes? Mm-hmm. Yeah, so the question is there bookkeeping overhead? Absolutely, there's jitter in the network, so packets can get delayed, and so we have to deal with the fact that there might be bursts that could occur. We also have to deal with the fact that there may be other users of that 1 gigabit link. And then we also have to deal with the fact that the recipient might be my phone. Right? And I could easily fill the entire memory of the operating system on this phone in fractions of a second at that rate. So we're going to want to balance that. And that's where flow control comes into play. And that's where we get a lot more bookkeeping. Okay, but roughly, when you're trying to figure out what the window size is supposed to be, it's going to be proportional to the bandwidth of the link or the capacity and times the delay. This is called the bandwidth delay product, because you multiply the bandwidth into the delay, and that'll give you, what you want to set your window size to. All right? So now let's introduce errors, because that makes it more fun. So there are 2 ways we could deal with errors. Errors in this case is a lost packet or a lost acknowledgement. The first approach is called go back N, and it means just that. We're going to go rewind back N and retransmit. The other is selective repeat. Now, if there are no losses, these 2 protocols behave identically. Just as I showed you is exactly what happens. With go back N, you're allowed to transmit your window, so your window size here is N, so you can transmit up to N unacknowledged packets. And then if you get a timeout for a particular packet, you don't get the acknowledgement for K, then you're going to retransmit packet K plus 1, all the way up to the end of your window. All right? Now, typically this will use a NAC-based approach instead of an ACK. So it'll say the receiver will send back a NAC, I didn't receive packet K, and then you just retransmit K plus 1, and so on. All right? The NAC tells you the first packet that you didn't receive in sequence. Okay, so let's look at an example. So here, same example we just saw, but packet 4 gets lost. All right, so what's going to happen? Well, packet 5 arrives. Right? Now, our out-of-sequence packet window at the receiver grows, right? Because we were expecting 4 and didn't get it. So we're going to have to hold on to 5. We can't give it to the application. And then packet 6 arrives, and we have to do the same thing. We have to hold on to it. All right? Now, a timeout will occur for packet 4. Right? And then we have to assume it's lost. And so now we may also, as an optimization earlier on, get a negative acknowledgement for 4. Right? But even if we do get a negative acknowledgement, we can't retransmit the packet. Right? We wait until the timeout and then transmit it. Now, why don't we retransmit it earlier? Any ideas? Yeah. Exactly. Remember that the network could be doing reordering. So it might be that we received 5, we received 6, and then, oh, here comes 4. It took the slow boat, around the different route and eventually arrived. So we wait for the timeout before we retransmit. So we're being conservative about when to retransmit. If we were being very aggressive, we would have retransmitted as soon as we got the negative acknowledgement. But if the network's reordering, that's bad, because that means we'll retransmit too much, and that will impact our throughput, right? Because we're sending the same data again. And especially in this case, right, where we retransmitted 4, 5, and 6. So we're going to really hurt our throughput. So this is called good put. How many bytes are you delivering that are good bytes at the end of the day? Here, we might be filling the link, but we're wasting it because we're retransmitting 5 and 6. Yes, question.
We got to Max saying we didn't properly send 4, and we're holding out until the end of the timeout to send it so that we don't flood the bandwidth. How would we tell that it just got reordered?
So the question is, how would we know if it got reordered if it was just delayed, and even though we got these negative acknowledgments? Because we could get a positive acknowledgement saying, I got 6. Right? And that tells us we got all the ones before it. So if that arrived before the timeout, then we wouldn't have to retransmit 4, 5, and 6. Yes? So the question is, if we don't want to overwhelm the network, why are we transmitting these negative acknowledgments, multiple of those? Those are small. They're like about 40 bytes, right? Whereas the packet we're sending might be, say, 1,500 bytes. But there's definitely an overhead. Communication, requires checksums and packet headers and things like that. So there's definitely an overhead associated with any packets that you send. Was there a question? So the question is, how does the receiver know what order it's supposed to receive things in? Every packet has an ID number, a sequence number, right? So if I received 4, I expect to receive 5 next, and then 6, and then 7, and so on. Question in the back?
Yeah, so why are we sending max when we receive 5 and 6? Why can't we just say that, like, I got 5 and 6, and then once the timeout for 4 hits, we only have to reset 4 back? Like, we should have to reset 5 and 6 as well.
So the question is, why do we have to receive 5 and 6 as well? This is go back in. So we go back in. So when you get a negative acknowledgement and a timeout occurs, you roll back and retransmit everything. The assumption here was, this was one of the first implementations of TCP. The assumption was that when you have losses, you tend to have bursts of losses. And so you just retransmit everything to get through the burst of the losses. Yes?
What happens if the NAC gets lost?
What happens if the NAC gets lost? Well, we're sending multiple NACs, but in any case, we're going to have a timeout, which is going to cause us to retransmit from the sender in any case. Yes? The question is, why do we keep 5 and 6 in the receiver's window if the sender is going to resend them? Because they might get lost. Right? The sender resends them, but if the network is noisy, they could also get dropped. And this way, we already have it, so we might as well not drop it. We've allocated the memory for it. Yes? Depends on the question is, are NACs or only NACs being sent, or NACs and ACs? depends on the particular variant of TCP. There's like, I think about 3 or 4 different variants at least, which tweak this settings various ways. You'll see them in a moment. The names are, might look a little familiar. Okay, any other questions? Yes?
So not receiving an ACK could also cause you to roll back.
That's right. Not receiving an ACK can also cause you to roll back. Okay, so an alternative that's rather recent, in the last, probably in the last decade roughly, to go back in is selective repeat. And this was made under, it took a long time for this protocol to be accepted and widely deployed. I think it was one of the service packs for XP that brought it to Windows. So that tells you, kind of how recent it is. And it was mainly because there was a recognition that networks were pretty good at most times not reordering packets. When a packet was lost, it really was lost. It wasn't matter that it was just kind of delayed and sent by a different route, and so it showed up much later. So here, again, it's a window protocol. We allow the sender to send up to n unacknowledged packets. And if we assume a particular packet gets lost, like packet K, the receiver indicates, I lost packet K. I didn't get it. Right? And it uses acknowledgments to do this instead of negative acknowledgments. And the sender just retransmits packet K. Nothing else. So, coming back to our picture here, I don't get packet 4. So I send an acknowledgement for packet 5 when I receive packet 5. I then send an acknowledgement for packet 6 when I receive packet 6. When the sender receives the acknowledgement for 5, but not 4, it knows 4 was lost. So it sends, or the acknowledgement for 4 was lost, so it sends just 4 again. Right, so that's here. And then I'll send back an acknowledgement for 4. Right, and once I do that, now my window can slide all the way forward because I know 5 has been received and 6 has been received, so it can become just 7. All right? So this is much better at retransmitting less as long as the network isn't busy reordering things under the covers. And again, with most modern networks, reordering is not an issue. Yes?
Could we adapt this to be better than the go back N, even in the event that things are reordering, just by also doing that timeout that we had before? So instead of we get an ACK for 5, oh, we must have lost 4, just we got an ACK for 5 but no 4, wait a timeout, then send 4.
Yeah, so the question is, could we make this better than even go back N by waiting a timeout before we retransmit? The downside of that would be delay, right? So as soon as we receive this acknowledgement that tells us there's a gap, we retransmit, as opposed to perhaps waiting until much later and then retransmitting. So it's much more aggressive on the retransmission with the assumption that there isn't reordering. So if a packet gets lost or an acknowledgement gets lost, it really was lost and not just delayed and reordered. So this is why it was somewhat controversial, because you're making this assumption, and if the networks don't meet it, then you could end up with lots and lots of retransmissions occurring that are spurious retransmissions, not valid retransmission, or necessary, I should say, retransmissions. Yes?
So in the previous go back N example, we kept the 5 and 6 from when we got them earlier, and the protocol just says reset 4, 5, and 6.
That's correct.
And then we just keep the 4 out of that, and that's why the window went blank. Then we had 4, 5, and 6. So we can receive them out of order to receive 4 after 5 and 6.
That's right. So if we go back to go back N, we keep the packets that we've received out of order. We're allowed to receive anything within our window we can receive. And our window size is 3. So we're expecting 4 at this point. We get 5. That's within our window of 4, 5, 6. We get 6. We can keep that also. If we got packet 7, we'd have to drop it. It's outside our window. Yes?
So is then the window that the receiver has, is it 4, 5, and 6, or just the one that's received?
The window has, yeah.
We made it look like the window was all the available ones we could receive. But here, you're saying it's empty. Like,
Yeah.
the first one should be 1, 2, 3.
Right. So the question is, what is actually this window has 3 slots. Slot 1 is empty. The first slot of the window is empty. the second slot has 5, the third slot has 6. Right? So we've reserved the buffer space. We'll see this in a moment, I think after the break. We'll see exactly how we kind of keep track of all of this. Any other questions? Okay. So summary. So TCP gives us this reliable byte stream. We open a connection with this 3-way handshake. When we want to close the connection, there's not an ideal solution because of the general's paradox makes that impossible. So we have an approximation that allows us to close the connection in all but sort of the worst Byzantine cases. We have reliable transmission is one of the other things that TCP provides. And a very simple version of reliable transmission is stop and wait. Not very good because it does not work well on links that have a high bandwidth delay product. So instead, we use a sliding window protocol, but as we've just seen in the last couple of minutes, it's a really complicated protocol to implement. So it works. It's much more efficient, but it's very complex. Questions? OK, so again, I want to revisit this slide because Professor Canning put this up right before we had Project 2 due. This is a class that is all about collaboration because as a computer scientist, that's what you're going to do in your job. You're going to have to work with other people. So we strongly want to encourage people to collaborate where appropriate. Now, where is it appropriate? When you're talking about designs, when you're talking about algorithms, when you're trying to figure out strategies for doing white box, glass box, black box, gray box testing, those are all things that we want you to collaborate on. Also, if you finished your code and you got it working a week early and somebody else is having trouble getting their code working, helping them get their code working is a very productive thing to do in this class and something we strongly want to encourage people to help with. What's not OK? Use common sense, right? So if you find solutions from somebody who took this class a couple years ago online, that's not an acceptable solution. Even looking at those is not, because that's going to cloud the way and color the way that you actually do your implementation. It turns out these projects have enough flexibility in the way you can do things that it's like a fingerprint when someone writes their code. In fact, it's a good enough fingerprint that we can actually compare against the submissions that people have done in prior years. All right? So we did that. We found over 25% of the groups in this class are copying code from online solutions. That's not acceptable. All right? So we're offering you an option. You can notify us that you are doing that. The deadline for that is tomorrow before midnight, and we'll go lenient. That means you'll lose credit for the code portion, at least lose credit for the code portion of that project. If you don't, you risk losing all the credit for the project and potentially failing this class if we have to go to you and ask you that question. We know who is being honest in this class and working very hard. We know who isn't. So we're giving you the option to come to us, email us, and make an appointment to see us, and we will be lenient. Okay? Now, I know this is a really hard class, and so there are a lot of us. Right? We have 6 staff in this class. That's 12 hours of office hours a week. And there are some students who are having trouble, and they come to our office hours every week religiously, and they go to multiple TAs' office hours. There are other students, there are others of you who I know are having a very tough time in this class and are not taking advantage of that. There's no reason. We're all very approachable. We're all doing this because we want you to be successful in this class. So there's no reason that you should do poorly in this class, and no reason that you should really need to resort to looking at prior year solutions. We will sit with you and get your projects working. Now, you got a message earlier today from, actually, I think just before class, Suzanne sent out the message, because as we've been talking to the groups that are involved in this unpleasant process. It's proven to be extremely stressful for the students. This is already a stressful time to be a student. And we want you to be aware, and Suzanne wanted you to be aware, that there are lots of resources that are all confidential, all free, that you can take advantage on campus. So even if you're not one of the students involved in this, if life is difficult right now, there's no reason not to stop in and see Christine. Okay, so hopefully this will not be a topic. Collaboration should be very clear, and hopefully it's not be a topic we have to revisit again. With that, we'll take our 5-minute break. Okay, I still have a lot of slides to go through, so we're going to get started a little bit earlier. All right, so flow control. The challenge here is we want to make sure a fast sender does not overwhelm a slower receiver. Right? So we put a buffer effectively between our producer and our consumer. So fresh out of lecture 5, you can remember that far back. We've got the producer putting things in the buffer, the consumer taking things out of the buffer. So with TCP, I didn't quite tell you the truth. Right? So the sliding windows, we're doing those at the byte level, not the packet level. So for simplicity, I used packets. But from now on, everything is going to be in bytes, and that's what TCP really does. So there are many variants of TCP that implemented Go Back N, TCP Tahoe, Reno, and New Reno. You can kind of see a naming trend that the Berkeley folks had. And then the version that did selective acknowledgement was called TCP SAC, for selective acknowledgement. Now, the receiver will tell the sender how many more bytes it can receive without overflowing its buffer. This is called our advertised window. So now, when we send an acknowledgement, the acknowledgement tells us the number of the next byte that the receiver is expecting, instead of the next packet. It's going to be the next byte that we're expecting. And that means the receiver has received, so if we send ACK for n, that means the receiver has received in sequence all the bytes up to n and including n minus 1. So now, flow control. So it's the same kind of producer-consumer relationship here, right? The sending process through its local operating system is filling a buffer in the operating system of the receiving host. That buffer is being delayed by, being drained rather, by the receiving process. Right? Now, TCP is implemented in the kernel, which means we don't want to be context switching every time we get in a packet. Right? Because 1 gigabit per second, we're receiving packets very, very quickly. So we're going to batch instead. Right? We're going to use buffers, and then the receiver will get a bunch of bytes out of the buffer all at once. So we can amortize the cost of context switching from the kernel into the receiving process. So we're going to use buffers to make all of this work. Now, we need buffers between the sending process and the OS and the other OS, and the OS and the receiving process. That's this picture. Right? Lots of buffers. So there's a buffer here, okay, because the sending process is producing bytes. The OS is draining bytes out of this buffer and sending them to the remote OS and filling this buffer. And then this buffer is being drained by the receiving process. So some assumptions. We'll assume our max packet size is 100 bytes. We'll assume the receiver can store 300 bytes in its receiving buffer. Right? And remember, the acknowledgement we send back is the next byte that we're expecting to receive in sequence. Right? Now, to make all of this work, we use circular buffers. So how many people have seen circular buffers before? Right, so not a lot. Circular buffers appear everywhere in operating systems, and especially within the network. We use circular buffers for everything. So we're going to assume we have a buffer that has size n. Okay? So here's our circular buffer, size n. And we're going to use modular arithmetic when storing things into the buffer. So a particular sequence number of our buffer data, so like 28, would be stored in 28 mod n plus 1. So 28 plus mod 10 rather is 8, plus 1 is 9. Okay? And so on. The key thing about circular buffers is they wrap around, right? So the ELLLO space WOR wraps around, and then L and D. Right? So this allows us to have a fixed size buffer that we can just keep circulating data through. Right? So we need to keep track of the start of the buffer and the end of the buffer. But everything else is just done through modular arithmetic to index into the buffer. So this is a much more efficient and simpler way of storing the data than, say, just keep growing and allocating more and more space, say, in the kernel. We have a fixed size buffer, and it just wraps around. OK. Now, with TCP, lots of variables we've got to keep track of. The last byte that was written by the sending process, the last byte that was acknowledged by the receiver, the last byte that was sent by the sender, okay, to here. And then on the receiver side, we have 3 more variables we have to keep track of. The last byte we receive from the sender, okay? The next byte that we're expecting, so the next in-sequence byte that we're expecting, and then the last byte that was read into the receiving process. All right, so flow control, oh, that's cute. Flow control basically keeps track of all of this at the receiver, right? So we have the last byte that's been read by the receiver, the next byte, so it's behind what we've actually received. Here's the last byte that we've received, and then we're expecting the next byte to come in here, right? And when we fill this, it'll wrap back around, right? Now, the receiver has extra space here, right? This is occupied by data that we're waiting for the receiving process to take, but the rest of this is available. And so our advertised window is the number of bytes that we can still receive. And again, it's going to be this white space in both sides. Right? So in this case, it's going to be the max received buffer size minus the last byte received minus the last byte read. Okay, we do this all with modular arithmetic, so it works. So now, over at the sender side, we have the last byte that's been acknowledged by the receiver. We have the last byte that's been written by the sending process. And then we have the last byte that's been sent. So here we've actually kept up, and we've sent the last byte that was written by the sender. The sender's window, the number of bytes it is allowed to send, is now going to be reduced. We're going to take the advertised window, instead of how much space we may have. The max send buffer now doesn't really matter unless it's smaller than the advertised window. we decrement the advertised window by the last byte sent and the last byte acknowledged. All right, so this is how we keep track of how much space in the receiver's buffer we can go and fill, and make sure we don't overrun it. Okay, this is still true if the receiver has missed data, right? Because the last byte read and the last byte received are not going to have changed. Right? We'll have a gap, but that's perfectly fine. Okay, the write window is how we limit the sending process. And it's now going to be a function of the max send buffer size. So it'll be the max send buffer size minus the last byte that we've written and the last byte that's been acknowledged. So again, it'll be the white space on the sender side. Right? Lots of variables we're going to keep track of on both sides. So let's say the sending app wants to send 350 bytes. And we're going to assume that we can only have packets that are 100 bytes in size. And the max receive buffer here is 300 bytes. So our initial advertised window is 300 bytes. All right, so 350 bytes get written by the process. Now we actually need to send them in the kernel. So first, we're going to send our first packet. All right, so our first packet goes out, and it's from 1 to 100. Right? So now our last byte acknowledged is still 0, and our last byte sent is updated to 100. Now it gets received here. Our last byte received becomes 100, because we got that in order. Our next byte expected is 101. So now we send back an acknowledgement. The acknowledgement is 101, because we expect to get byte 101 next. And our advertised window is now decremented, because we've got 100 bytes filling our 300 byte buffer. So it's now going to be 200 bytes more that can be sent. Okay, sender sends the second packet, and the receiver gets the next 100 bytes. We update our last byte sent. We update our last byte received, because that was in order. Next byte expected goes to 201. Right? So now we adjust our advertised window, right? Because the receiving process pulled out the first 100 bytes. And so our advertised window is still 200. Even though we've received 200 bytes, we only need enough space to store 100. I'm sorry, 200. We only need enough space to store this 100, which has not been received by the receiving process yet. Okay, so the other side, we can send our third packet, and it gets lost. Right, so what happens now? Our last byte sent goes to 300, and the sender stops sending. Right, we've sent 300 bytes, and our advertised window minus last byte sent minus last byte acknowledged goes to 0. Right? So now we get the acknowledgement for 101. Right? So the advertised window is 200. So this acknowledgement tells us the next byte that's expected, which is going to be 101, and that the receiver no longer needs, thus, the first 100 bytes. So we can drop them out of our window. Forget about them. Okay, we still can't send because the advertised window is still full. Right? We've sent 300, and we haven't been told that we can open up our window. All right. So now we get the acknowledgement for the second packet, and advertised window is 200. Right? Now we can send new data. Right? Because we know that that second packet was received, and the advertised window is 200, and so that allows us to send another 100 bytes. So we can send the last 50 bytes. All right? And that goes in. Okay. Now we get back an acknowledgement for 201, right? And an advertised window of 50. So since it still specifies 201, we know that it was out of sequence. Right? We know that it missed an acknowledgement. We expected to see 301. So can we resend that, even though the advertised window is 50, can we resend that packet? Right, that's a 100-byte packet, and the advertised window is only 50. What's that? Send only 50 of it. No. So it turns out, actually, we can send the whole packet because we already sent it. Right? So it was already allocated space was allocated for that packet. So we can resend it again. It's not going to make the window grow. So we just simply resend it again. All right? And then it gets it. Right? Now we'll get the acknowledgement back for 351, and we're done. Okay? No more sending. So I think at this point I'm probably going to stop. There's only a couple more slides, and you can look at them. It's basically a discussion. Right? But I strongly encourage you, take a look at the slides and work through the messages that are going back and forth and see if you understand how all of 6 of those parameters are being updated. And we'll also post some of the material from EE122 if you want to look at it a little bit more in depth. With that, any questions? Okay, see you on Wednesday. Bytes go from one tuple to another tuple. The tuple is the local IP address and local port to the remote IP address and the remote port. Now, I did say it provides this guarantee of reliable, in order, at most once delivery. But the real world is not perfect, and connections can fail. Right? So if I'm talking to the access point in this room and the power goes out, what are the odds of that happening? Then there's no way my packets are going to get through. And so when that happens, TCP will reset the connection. Right? So it's going to try, and it'll try, and it'll try. So even if I'm dealing with a noisy wireless network, the packets will eventually get through. But if it tries and tries and tries and can't get the data through, it resets the connection. So you'll see this with a web browser. You'll wait for a really slowly loading page, and then it'll say the connection was reset. That means TCP tried really hard and then gave up. OK, and then when we're done, we tear down the connection. So let's go through each of these processes. So first, we want to open the connection. So our goal here is between, yes, question?
You mentioned that it can be of arbitrary length.
Yes.
How do we know when we're going to close? Why would we ever close down?
So that's a very good question. These messages can be of arbitrary length, so how do we know when we can close the connection? That's why that's why we're going to actually spend some time talking about how you close the connection. And it's not, you would think it would be easy. You just say, OK, close the connection. But it's actually a lot more complicated under the covers. OK, so first we're going to open the connection. So we need to agree on some parameters. And in particular, the parameter we need to agree on is the starting sequence number that we're going to use. Right? Now, the starting sequence number is going to be the sequence number of the first byte in the stream that we're going to send. All right? So this way, when we get bytes at the other end, we can tell whether packets, we can tell whether they're arriving in order or not. Okay? If we didn't know what the starting sequence number was, we'd have no way of knowing. Projector with its little Ethernet cable supports the socket API. Laptops support the socket API. So it's in many different operating systems, including embedded operating systems. And then most languages support it. So obviously Java, Python, Perl, and so on all support the socket API. It's very similar to the file API that we have in Unix. So you actually have a socket descriptor, which is very similar to a file descriptor. It's a handle that gives you access to a socket. And then you can use read, write, and close system calls also on a socket. All right? Now, the transmission control protocol is built on top of the sockets layer. And it provides you with reliable, in order, at most once delivery. Okay, so lots of guarantees there. Yes?
When they were building the socket API, why didn't they build it on top of the file descriptor API?
So good question. When they were building the socket API, why didn't they build it on top of the the file descriptor API. It is. It shares a lot of commonalities in terms of the kinds of functions that you can do on a file handle. You can like open and close and read, you can do on a socket also. So it shares a lot of similarities. The difference is that there are some things that you want to do on sockets that are very different from what you would do on a file. You wouldn't wait for a file to appear, or wait, whereas with a socket, you'll wait for an incoming connection to appear. Or you'll make a connection to another remote machine. So there's some differences, and that's why it's not a perfect match. But a lot of the functions are actually shared between the two. OK, so you get all these great things, right? Last week we heard about IP was best effort delivery, which means maybe you get the packet, maybe you don't, maybe it arrives in order, maybe it doesn't, maybe it gets folded, spindled, mutilated. Not with TCP. With TCP, you get the packet, it arrives in order, you only get it once, you don't get duplicates, and it will be delivered. It's also stream-oriented. So you can all right, so we can get started. So this is a little loud. OK, so this is lecture 17 of Computer Science 162. So still kind of loud. Goals for today. Maybe that's a little better. So we're going to talk about the socket API. So this is the interface between applications and the kernel for doing networking. And then we're going to talk about TCP. And TCP contains 4 important components that we're going to talk about today. The first being how you open a connection, the 3-way handshake that occurs. The second being reliable transfer. The third being when you're done with a connection, how you actually tear that connection down. And there's some interesting challenges. It seems like it'd be really simple, but it's actually a very complex problem. And then flow control. What we're not going to talk about is congestion control. And this is a plug for going across the hall and listening in on EE 122 if you want to learn about how congestion control works in TCP. So let's start with the socket API. So I have a bunch of applications. So I have Mozilla, I have Firefox rather, I have Thunderbird, and I have Skype. Okay, so web browser, email, and a video conferencing application. They use the socket API to talk to the transport layer, the transmission control protocol, and the user datagram protocol. All right? And then those two talk to the internet protocol layer, the network layer. Now, where do you think the socket API was invented? Ah. Wrong answer. Sorry, not Stanford. Berkeley, right? Back in the 1980s, it was part of the Berkeley standard distribution. It is the most popular network API today in billions of devices, many, many billions of devices. Every smartphone supports the socket API. That can send arbitrary length messages across TCP. Whereas underlying that, IP is fixed size packets. Or I should say not fixed size packets, it's maximum sized packets. It also provides multiplexing and demultiplexing. So IP remembers between 2 machines. Right? Your machine has a unique IP address, my phone has another IP address, but there are many applications running on each one of those. TCP gives you the demultiplexing and the multiplexing to let those different applications both on my laptop and my smartphone talk to each other. Okay, so I could have a web server on my laptop and a web browser on my phone. I could have a mail server on my laptop and a mail client on my phone, and those both can work because TCP takes care of multiplexing and demultiplexing into IP. All right? And then you also get congestion and flow control. So congestion control is how we deal with the fact that, for example, if we're using a wireless network, it could be very crowded. And we want to fairly share that bandwidth across all of the different users of the network. So TCP tries to be fair when it's using the network. Then flow control is what we'll actually talk about today, and that's where I'm sending data at a high data rate from my laptop to my phone, or from my server to my phone, and this phone has a little bitty tiny RAM in it. So I don't want to overrun that buffer. And flow control is a way of the phone saying, hey, don't send me any more. And we'll see how that works. And then there's lots and lots and lots of applications that are built on top of TCP. All applications that want reliable communication. So you build things like chat. Right? You don't want to lose messages. So we can wonder about certain operating systems, whether they, certain mobile phone operating systems, whether they use TCP, because my messages always seem to get lost. File transfer, web browsing, all takes place over TCP. Any questions? Okay. So TCP as a service does the following things. First, we open the connection. There's a three-way handshake that occurs when we open the connection to set up that connection. Then we actually send our bytes. Right? And so again, now as a really simple security thing, and also to deal with repeated connections that I might make from one machine to another, we make the sequence numbers random. And so hopefully that means we don't have collisions. I don't get a packet that was delayed in the network from a connection that I just had from a particular host. All right? Okay, so the way this works is the server, the application here calls listen. Right? It says, I want to listen on a port. So if it's a web server, it says, I want to listen on port 80. If it's a server used to send mail, it says, I want to listen on port 25. Right? If it's SSH server, it says, I want to listen on port 22, and so on. All right? These are well-known numbers. If you go in your computer, if you have a Mac and you look in /etc/services, you'll see a list of all these well-known port numbers. Okay, at the client side, it says connect. Right? So this is, you typed in www.cs.berkeley.edu, and it connects to that machine on port 80. So it'll issue a connect. And the operating system will now send a special packet from the client to the server called a SYN packet. This contains its proposal for the first sequence number. Right? So we picked this random number, X, and we sent it. So that message arrives here, and when it arrives, the server application gets notified that there's an incoming connection, and then it accepts that connection. And now once it accepts the connection, the operating system now will send back a message containing a SYN and ACK, and a sequence number Y, and an ACK X plus 1. Right? So why does it send X plus 1 back? Any ideas? Exactly. It means that we have received the connection. Right? We received the X. So we're sending it back to say, yes, I got your X. Right? And now I'm expecting X plus 1. It also sends